Now see here self induction. Here if you have taken like this is a solenoid here, this is connected to here a battery like this and the resistance is over here. Now current is flowing from this side. When current flows through this loop or this solenoid, magnetic field is here inside it, that is B is equal to mu naught Ni, where N is the number of turns, I is the current. Now when the value of the current is changed, suppose current is increasing in this side, there is a I that is increasing in this side. So when current increases, magnetic field also keeps on changing, that increases. Because of that, magnetic flux linked with the each coil changes, as a result EMF is induced. So whatever the EMF is induced, that is induced in such a way which opposes its cause of production. So if the current is increasing, this side is here, so direction of the induced current or the EMF current is such, EMF is such that here that opposes its increase of the magnetic flux. And this EMF or induced EMF is also known as here back EMF. And also when you reduce the current in this circuit, EMF is induced in this coil in such a way that it opposes the cause of its production. It means when the current is reduced, magnetic flux reduces. So the induced current is such that which increases the magnetic flux. Because of this, again the back EMF or the EMF is induced here. So this EMF which is induced here in the coil, it opposes increase or decrease of the strength of current. So this phenomenon of this coil is known as self induction. So simply this is the property of the coil by virtue of which it opposes increase or decrease of the strength of current in the coil by inducing an EMF, and this phenomenon or this property is known as self induction. And now suppose current I is flowing through this coil, so the total magnetic flux is directly proportional to I. We can write flux is equal to Li over here, where L is known as coefficient of self induction. L is known as coefficient of self induction, or you can say simply self inductance. So this L is also known as self inductance. So now we can define this self inductance. What is self inductance? So if you take this phi is equal to Li, so you have written here phi is equal to Li, and if you are taking I is equal to 1, then you can write flux is equal to L. So now the coefficient of self inductance of the coil is numerically equal to the magnetic flux when the current in the coil is flowing, the current in the coil is unity, or the current is simply changed by unity. And SI unit of self inductance is, that is here Henry. So SI unit of self inductance is Henry, and that is represented by H. So now we have done here flux is equal to Li. So we can calculate induced EMF. So induced EMF is equal to minus d phi upon dt. So E is equal to minus d upon dt Li. So we can write E is equal to minus L di upon dt. So this is the induced EMF in the coil. If you are taking di upon dt is equal to 1 ampere per second, then you can write minus E is equal to L. It means coefficient of self inductance of a coil is equal to induced EMF in the coil when the rate of change of current is 1 ampere per second. So now we have done this is about the self induction, and now you have to do here, you have to find out actually the coefficient of self inductance of a long solenoid. Now see a self inductance of a long solenoid. Suppose you have taken a long solenoid like this, current I is flowing through this, N is the number of turns per unit length, and L is the L is the length of solenoid. Now, when current I flows through this, magnetic flux linked with this whole solenoid or the long solenoid here. So, is when current, we can write when variable current I flows through the solenoid, then total magnetic flux solenoid is given by phi is equal to Li, where L is called coefficient of self inductance. So, we have got the first equation phi is equal to Li. Now, see here current I is flowing through this, and already we have assumed N is the number of turns per unit length and L is the total length of this. So, we can write magnetic field inside this is also, that is B is equal to mu naught Ni, where I is the current flowing through this and mu naught is here the magnetic permeability of the free space, N is number of turns per unit length. Then magnetic flux through one coil, through one loop is equal to, we can write B into A. So, that is mu naught Ni into A. A is the area of cross section of the loop. Then we can write total magnetic flux. Total magnetic flux is equal to here mu naught Ni A into NL. This we can take the second one. NL is the total number of turns in the solenoid. And now already we have got the first equation where we have written Li is equal to, this is also flux, Li is equal to mu naught Ni A into N square into L. I and I will get cancelled. You will be getting L is equal to mu naught N square A L. So, this is the self inductance of the solenoid. And now we can solve it, simplify it also. So, we have taken L is equal to mu naught. In place of N we can write N square upon L square into A into L, this cancel. So, L is equal to mu naught N square A upon L, where capital N is the total number of turns in the solenoid. And also see here the self inductance of the solenoid depends on the geometry of the coil, that is the number of turns, area and length, as well as magnetic permeability. So, if you place some thing is here like a solenoid you have taken, and if you placed here the soft iron inside it, which has got permeability, relative permeability mu r, then L will become mu naught mu r N square A upon L. So, this is the formula for the self inductance of a long solenoid.